Okay, this is a video for Math 2413, Calculus 1, for September 16th. And SalCon does not have a video on the topic that I want to go over today, so instead I will make the video myself. Now there's a lot of things about Sal's style that I like, so I'm going to implement those here today in this video. And of course, since I like his style, that's why I'm assigning his videos. I think he does a good job. So when we've been talking about the derivative so far, first of all we looked at it as the limit as h approaches 0 of the slope of secant lines. Okay? And then we looked at some rules, some shortcuts for the derivative algebraically. We've had the power rule, we've had the chain rule, and we've had the product rule. Okay, and it turns out that's all the rules we're going to need. We're going to need to learn a few more derivatives of trig functions and exponentials and logarithms, and then we'll get on to something called implicit differentiation, but we're at least halfway through those derivative rules. What we're going to talk about in this video today is the graph of the derivative. So when I have a function x cubed minus 2, we can compute its derivative. F prime of x is 3x squared in this case, using the power rule. Now what does that mean? That expression, 3x squared, gives us a slope of the tangent line for f of x equals x squared minus 1 at any x value we would want. So if I draw a graph of f of x cubed just looks like this. Okay, and this point is at the origin, so the minus 2 shifts it down. And instead the graph's going to look something like this. Okay, a very rough sketch. That means at any x value we can compute the slope of the tangent line. So if I were to draw a tangent line at, say, x equals negative 1, okay, that tangent line is about right there. Okay, I can find its slope just by plugging negative 1 into my derivative formula. So the slope of the tangent line at x equals negative 1 is f prime of negative 1, so that's 3 times negative 1 squared. It's a pretty steep line, and we see that it does have positive slope, like we would expect, because we see the line goes upward, and the slope ends up being exactly 3. And we've done some problems where we can find the equation of that line, even. So the derivative tells us what is the slope of the graph at that point. Okay. Now what I'm going to do is look at the graph of the derivative. So I'm going to redraw the graph of my function and draw it a little bit bigger here. So here's f of x. We've got x, and then f of x, and I know it looks like a cubic that's been shifted down too. Now what's the graph of the derivative going to look like? Okay, so I'm going to put the graph of the derivative below it here. And I'll use a different color for the derivative. We'll try red. Alright, well, first place I want to start is at x equals 0. If I look on the original function, the tangent line, well, it should be flat. Here it looks like it's got a little bit of positive slope, but for x cubed, the tangent line at this middle point is flat, so it has slope 0. Our graph flattens out there. So when we graph the derivative at x coordinate 0, okay, we have a derivative of 0. So the y coordinate on the graph of the derivative will be 0. Now what if we go out to 1? At x equals 1, the tangent line looks something like that, and the slope's positive. Now I can use the power rule to compute exactly what that slope is, but that only works if we have a function that we know how to do the derivative of. There's lots of functions that we don't know how to do the derivative of yet, so we can't actually compute that number, like trig functions, like logarithms. And there are some functions out there that are very hard to do, even once you know all the rules. Whatever this derivative is, it's positive. Not only so, but as I go more to the right, it gets steeper and steeper. Okay. This is some positive value m, so the point on the graph of the derivative is going to be 1, some positive value. The y coordinate is equal to the slope of that secant line. Now, as I go into the left, closer to x equals 0, the slope is flat. The tangent line is flattening out, which means the slope is decreasing. So it ends up being that the function looks like this for the derivative. Something like that. Okay. Now what happens over here? Notice that the graph is still increasing. It still has positive slope. So if I look right out here, okay, this has positive slope, because if I draw the slope or the tangent line here, the slope would be some positive value. So at this x value, the graph of the derivative will have some positive y-coordinate. I don't know, maybe it's, that doesn't look quite as steep as the other points, so maybe it's something like this. Okay, and it just keeps getting steeper as I go over to the left, so it's going to look like that. So my function, x cubed minus 2, had derivative 3x squared. And you can see here why it ends up being a parabola. The vertex on the graph of the derivative, that's at the origin in this case, refers to the point of the function where the derivative is 0, where the graph flattens out. And then since the derivative is positive for every point that's not the vertex, that means that for every point that's not at x equals 0 right here, the slope is positive. Okay, the slope of the tangent line is positive. So what we're graphing here is the slope of the tangent line at the same x value. I'm going to do a few more examples, and I hope that'll help to clear this up and get you going on that worksheet. These are examples we haven't seen before. Computing these derivatives using the formal definition, the limit as h approaches 0 of f of x plus h minus f of x over h, is very cumbersome. It takes a lot of work. You got to use trig identities, you have to use a nice geometric construction, and we're just not going to take the time to do that in this class. What we're going to do instead for the trig functions is look at their derivatives graphically. So let's take, for example, sine of x. The graph of sine of x, let's see how good I can do this, looks something like this. Right. So what is the graph of the derivative going to look like? Well, I'll draw me some coordinate axes here, and we're going to get a very rough shape for the graph, and it's going to imply that the derivative might be this certain function, and I'm just going to have to tell you that it does, in fact, end up being that certain function. We'll go to green for the derivative. Now, what's the derivative at the origin here? Well, the derivative at the origin is not 0, because we're not looking at the y-coordinate. We're looking at the slope of the secant line. The derivative at x equals 0 for this function is some positive number. So the graph of the derivative will have a point at 0 and a positive number, whatever the slope of that secant line is. If, however, we go over here, and that ends up being pi over 2, x equal to pi over 2, then we do have a derivative of 0. Anytime you have a max like that, where it is at the top of a hump, the tangent line is positive. Or, excuse me, the tangent line is flat. It has the slope 0. So if I graph the derivative, the y-coordinate is going to be 0. Alright, if I go to this point, now the graph is going downward. Right, it has negative slope. So if I graph the derivative, it's going to have some negative y value. The y value here is equal to the slope of the graph at that point. Okay, the slope here ends up being 0, and we end up right back where we started. This is the same situation as over here. So I've got some positive steepness here, and then the derivative here is 0. That tangent line will be flat. So since the slope of that tangent line is 0, the y-coordinate of this point will be 0, because the y-coordinate is the value of the derivative at that particular x. And then this is going to be a negative slope. Okay. Slope ends up being 0 again here, and then the slope ends up being positive again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points for the graph of our derivative. And if we connect those points, we find that the graph of the derivative is going to be something like this. And notice that the derivative, for example, here is at a peak, because if I look back to the original function, it's steepest at that x value. The derivative is still positive for x values just to the right of that, but it's not quite as steep. Okay, so the slope of the tangent line is going to be a little bit less. In other words, the y value is going to be lower. Alright, so if the function is sine of x, what is this function? Well, this just looks like a shift of sine of x, and indeed it is. It's a horizontal shift, but this ends up being exactly cosine of x. So if our function is sine of x, graphically, I've tried to give some kind of justification that the derivative does end up being cosine of x. Now, I haven't proved it, because I haven't shown you, for example, that the derivative here is actually 1. It ends up being 1, and I'm just going to have you take my word for it at that point, or at this point. But through the graph, we can see that the graph of the derivative should indeed look something like cosine of x, and that ends up being correct. Okay, let's do one more example, and that will be to find the derivative of cosine of x. We've already found the derivative of sine of x, so now we'll find the derivative of cosine of x graphically. So cosine of x I just had graphed as the derivative of sine of x. There's x. And it has peak on the y-axis, and it looks something like this. One thing I should mention is that these derivatives only work if you're measuring your angles in radians. If you're using degrees, the derivative ends up being a lot more complicated, and we'll probably have a problem along those lines. So what happens to the derivative? What is the graph of the derivative for cosine? Alright, well, like before, we'll just plot a few points and try to get a sense of the shape of the curve between those points. Well, I've got a peak at x equals 0. So that means at x equals 0, the derivative is 0, so there's a point at 0, 0 on the graph of the derivative. I better switch to a different color. How about pink? Okay, also over here at x equals pi, we have derivative 0, so if I go down to the graph of the derivative, that derivative is 0, x equals 2 pi, the derivative of cosine ends up being 0, and the same for negative pi and negative 2 pi. Now, what happens between x equals 0 and x equals pi? Well, what happens between x equals 0 and x equals pi is that the slope of cosine is negative. And it's steepest right when it crosses the x-axis, which is at pi over 2. Since it's negative, the derivative is going to be below the x-axis. So if I graph the derivative, the y values correspond to the slope of the function. And since it was the steepest at pi over 2, that's when it's going to be the furthest down. Alright, now between pi and 2 pi, the derivative is actually positive. Alright, so it's going to go back up. Alright, same kind of thing over here, and we learn that the pattern just continues. And we end up with this graph. And what is this graph? It's not sine of x. Sine of x, if you'll remember, does go through the origin, but it goes this way, and it peaks and it comes back down, etc. This is sine of x flipped over. And we learned that the derivative of cosine x is the opposite of sine of x, negative sine of x. We did that graphically. Okay, so there's two facts. The derivative of sine is cosine. The derivative of cosine is negative sine of x, and we saw that using the graph of the derivative.